Welcome back, my dear friends. A very good morning, good afternoon, good evening to all of you wherever you are in this part of the globe. And this is the DADM 3, which is Data Analysis and Decision Making 3 course under NPTEL MOOC series. And as you can see, and as you know, I will not use the word see, this whole course duration is 12 weeks, total contact hours is 30, which when converted into number of lectures is 60, because each lecture is for half an hour. And we are going to start the 4th week, that means we have completed 3 weeks. So, by the time you are going to listen to this lecture, it is almost the same time where you would have taken the assignment 3rd. That means, after each week of 5 classes you have 1 assignment. So, we have already completed 3 assignments. And as you know, this being a 12-week lecture, you will have such 12 assignments, and after the end of the whole course you will be taking the final examination. And my good name, as you can see on the slide, it's and I will repeat it, is Raghunandan Sengupta from the IME department at IIT Kanpur. So, if you remember, we are considering the concept of a basis or a vector and spanning. So, that means and the later part of the last lecture, which is the 15th one, I kept repeating in the concept of rank of a matrix, which is in a very simple sense is the number of such equations which are required to basically express the rest of the equations. So, if rank is exactly equal to the number of equations which you have, which is equal to the number of variables, that means that you will have basically have a unique solution. Now, when converted into the concept of vectors, it is basically the minimum dimension of the vectors based on which you can span or spread and find out each combination of the vectors which are there. So, this is more from the mathematical point of view, but when it comes to the actual implementation point of view, the simplex method by Danzig, it exactly uses the same concept which I am just repeating it. So, as we are going to start the 4th week. So, the slide shows you the 4th week, which is the lecture number 16, which is the first lecture for the 4th week. Now, what we need to solve actually when you come to the matrix multiplication concept and the basis solutions in simplex method proposed by Danzig, the precursor is you have n number of equations to solve and n number of such variables to find out. So, m or n which I am talking about is basically the number of rows, which is the number of equations, and n, the column, is the number of variables. So, if m and n are same, then the number of, and none of the equations can be expressed as a unique combination of the other, you will have a unique one solution for all the x's. But that will come later. So, actually what you have is, you have in the matrix concept a matrix A multiplied by x, which is a vector, that is equal to B, which is also a vector. So, if the dimension of A is m cross n, the dimension of x has to be n cross 1, because it is a vector, and the final result is m cross n multiplied by n cross 1 would give you basically m cross 1. Hence, the dimension of B, which is on the right hand side, would basically be m cross 1. So, let me go back what I read, let me go back to the slide. B, where A would basically have the parameters based on which you will basically multiply x's values, and B are basically the right hand side of the constraints, and x as the decision variables which you have, or the values you want to find out for the variables. So, A x is equal to B. So, this equality which is coming out, if you remember in many of the constraints they are less than type, greater than type. So, those are immaterial, because they can basically be brought down into the equality sign using very simple concept of addition and multiplication of variables, which we will consider as slack and surplus, which will make things very clear to you. So, A x is equal to B is to be solved, where A is of dimension m cross n, m number of rows, n number of columns, x is the size of n cross 1 and B is size m cross 1. Thus, we are going to utilize this concept. Now, this is very important, even though I have not written it here, it will become clear. Thus, we are going to use the concept of pre-multiplying A with its inverse or post multiplying A with its inverse. The post multiplication of A with its inverse is not shown here, but pre multiplication, post multiplication, the inverse should be exactly equal. So, pre-multiplying A or post-multiplying A with this inverse would always lead to the identity matrix I. So, once the whole process of multiplication on the left hand side, you are doing some calculation, you are converting A slowly, you are converting the rows or the columns however it is, slowly A gets converted into I. Now, the same process of steps you are also doing on the right hand side, because you want to balance the equation, right. Just like you balance the weights, if you take out something from the left balance weight which you have, then you basically take out the same quantum of product from the right hand side of the weighing scale. If you want to add, you add. So, you are just doing the balancing act, like you have two buckets and of water and you are trying to balance. So, taking out some water or fluid from the left bucket would also result in the same steps being taken there. So, as A is being converted into identity matrix, the same operations of the rows and columns are being done on B. The reason being that when you are pre-multiplying A with A minus or post-multiplying A with A minus, you are doing the same thing on the right hand side. That means, pre-multiplying B with A minus or post-multiplying A with B with A minus. So, at the end of the whole process, step by step which you do. Why I am saying step by step? Because if you go back to the fundamentals of matrix multiplication by inverse, what you do is basically you find out the determinant and the concept and trying to find out the transpose considering the row and column are fixed such that the end result gives you the A minus. So, each and every step you do that. At the end of the results, on the left hand side you have x only pre multiplied or post multiplied by I, that is immaterial, I is 1 only, and the right hand side you have A minus A invert A minus into B. So, hence the concept of row and column is maintained, and post multiplying or pre multiplying would give you the same answer. So, hence when the whole process is done, so x is basically a vector. On the right hand side obviously you will also have a vector. So, the end of the results would be the first element of x, which is x1, would be equal to the first element of the combined combination which you have A inverse A, not my A minus A inverse into B. Similarly, the second element which is x2 will be equal to the second element on the right hand side. So, the whole operation would give you the unique values of x, hence those would be the solution based on which you can find out the simultaneous equation. So, this concept will be utilized time and again when we use the concept of simplex method proposed by Danzig, that is all. The concept of Gauss-Jordan concept. So, let me read the second bullet point. Thus, when we use the concept of A inverse A, that will give me A inverse B, and once the whole operation is done, I will have I x, which is identity x is equal to A inverse B, such x would be given by the elements of A inverse into B. Now, you want to start the solution. So, that solution based on which you will start the starting point. If you remember in that initial problem, I started at the origin. So, that would basically the starting point. So, that will be considered as the basic solution. Now, whether the origin of the basic solution based on which we are going to start is one of the corner points in the feasible set, that has to be noted down, because if the 0 point is not amongst the feasible set, then trying to start your problem from the 0 point or the origin does not make any sense. So, first you have to check the point based on which you are going to start off your iterative process, that means the point depending on from where you will start your slope ascending or descending depending on whether there is a maximization problem or the minimization problem, will depend whether that corner point is one of the feasible point in the overall space. And as you start moving, you will all traverse the feasible points only, because if you start from an infeasible point, then trying to come back into the feasible region may not be possible, that is not doable. Hence, we have to basically check the basic feasible solution is a doable one based on which we start the process. So, consider basic solution, consider a system of m simultaneous equation in n unknowns. Now, this is important to note. If I remember, I have mentioned that in the last class at some point, which is in the 15th lecture, that you have m number of equations and n number of variables. So, if m and n matches and all of the equations are unique, none can be expressed as a convex combination of the others, you have a unique vector of solutions of x1 to xn. Now, if m and n are different, so it would mean that either m is more or n is more, that will give you two different pictures. So, here we will consider that m and n are different, later on we will find out that whether m is greater or less than n. So, consider a system of m simultaneous linear equations in n unknowns. In that case, Ax is equal to b is the actual equational format which we have to have. So, and here it says that m is less than n, hence the rank of m is m of A is m, that means the minimum. So, technically it would be the minimum of the number of rows and columns, and it can be proved. So, we will consider the minimum size of m or n depending on the convex combination such that it is able to express all the rows or columns by that convex combination which you have. So, the row operations and the column operations, if you remember in matrix multiplication, is exactly what we will try to utilize. So, I was trying to hint at that, I am sure you will have got it. So, then what you will basically have is, considering that m is less than n, you will take a set of m cross n m which is n mango, n as in nose. So, then an m cross m non-singular matrix, non-singular means that the concept of determinant would exist, or else if you want to find out the inverse and if the determinant does not exist, then that is a problem. So, then m cross m's non-singular matrix is chosen from A, and if all this rest of n minus m n, so n is more, so consider m is 10, n is 20. So, you will 10 cross 10 number of variables and equations and express the rest 10 by the convex combination of them. So, let me read it. If all the n minus m not associated with the columns of this matrix which you have considered as to be independent are actually set to 0, because they are not to be expressed, you consider those variables to be 0, then the solution to the resulting system of equation is called a basic solution. Whether that basic solution is feasible or not, we have to check, which I mentioned few minutes back. These m, now remember, this m has to be unique, it need not be only unique in the sense from where you start, and also remember this m is, I should not be using the word unique, that means only one set of m combinations which are there, they can be different sets, but the combination of all of them is always m in size. Now, which m you will choose such that your starting basic feasible solution would lead to your optimum solution is also a point, but we will still consider the initial that the basic solution would be there. So, the m variables which can be different from 0 are called the basic variables. So, say for example, I have x1, x2, x3, x4, x5 as the number of n, and out of this, if that means x1 to x5, which is 5 is n, and if I am able to express that set of equations as 3 cross 3 vectors I take. So, these 3 variables considered is x1, x2 and x5 are non-zero, while if I mention x1, x2 and x5 are non-zero, then I will consider the variables x3 and x4 are 0, such that the vector based on which I will start off the solution would have x1 a non-zero value, x2 a non-zero value, x3 a 0 value, x4 a 0 value, x5 a non-zero value. So, based on that I will consider a basic solution and start. Now, it does not mean that I can also have a basic solution where I can start of the solution can be x1, x2 are 0, x3, x4, x5 are non-zero. In that case, the vector based on which I will start on my solution is the basic solution can be x1 is 0, x2 is 0, x3, x4, x5 are non-zero. So, this is possible. In optimization problem, one tries to find the best possible allocation of resources. So, I will basically now go into the general formulation and then again come back to the solution technique. So, it is basically I have given you the general feel how you will solve that, but how the greater than less than values would be considered, I will basically state in a very general format. So, whenever we are solving an optimization problem, our main concern is to find out the best possible solution of allocation of resources. So, resources can be, say for example, trucks, resources can be, say for example, some food material you want to give to different people or children who are undergoing some malnutrition treatment required, or it can be, say for example, resources you want to allocate to different states in India to build a bridge, or you are the CEO of a company and your resources are constrained and you want to build up, say for example, 5 roads and you are in the civil construction. So, that would also mean that resources are there which you want to optimize in the best possible manner. That optimization would basically come as a maximization or a minimization problem. So, it means that best possible allocation of resources amongst the probable set of alternatives which are there. So, these alternatives which I mentioned at the corner points, the whole set is the feasible region. So, the corner points would be the search set where I will basically restrict my search. So, they would be feasible set, and we want to find a unique combination of the control of the decision variables subject to some restrictions or constraints on the control variables, like say for example, 2x1 plus 3x is less than or equal to 8. So, in the problem of trying to solve for the machines, the machine utilization is maximum in a day is 8 hours, or one person cannot work more than 8 hours. So, in that case the constraints would basically specify that 8 hours is there, how you will basically try to utilize the machines in the proper manner to get the optimal solution. So, you have restrictions and constraints on the control decision variables in the domain space in order to basically optimize a given objective function or a set of objective functions, considering it is a multi-objective problem. So, this is the statement, and then let me write down the problem in the very simple manner. The equations does not look ominous, they are very simple. So, our general optimization problem. So, these variations of the problems will be occurring later on. So, one can be simplex method, one can be 0-1 programming, one can be integer programming, one can be goal programming, one can, and then we can bring the concept of time, basically solve it as a dynamic programming. It can be stochastic programming considering the distribution of the variables which are there or the parameters which are there. Then one can be mixed integer linear programming. So, there can be different combinations. So, I will consider you want to optimize some objective function, and if you see I here, if I is 1, it is a single objective function based on which we are trying to solve the first set of the problem. If there are more than 1 i's, you will basically have f1, f2, f3, that means you will basically have a multi-objective problem. If it is 2 objective, it will be a bi-objective problem. Now, on the constraint sides, I will basically differentiate. Here I am trying to differentiate, but in the later part when we solve the linear programming, they would basically be only one set of constraints. Some of the set of constraints, why I am differentiating that, you will understand later on when we do the probabilistic problem. So, you have once a j number of sets of variables which can be greater than type, less than type, equal to type, and you have gj's depending on x with the decision variables. D is the deterministic parameter. We are not going to consider the deterministic parameter for the initial major part of the lectures. P is the parameters which are non-deterministic, and again we are not going to consider the set of non-deterministic parameters in the first huge number of set of lectures which you have. And B is basically, Bj is basically the right hand side of the constraint which you have. So, initially this J number, capital J number of constraints which I have, initially we will consider them deterministic, but later on we can change them to the probabilistic also, such that we will be able to solve the reliability part and the robust optimization problems as such. The second set of constraint, which is capital K in number, small k is equal to 1 to k, are the deterministic constraints. So, I am trying to differentiate the deterministic and the probabilistic in this simple formulation, but when we solve the problem we will do away with the probabilistic part. So, you have capital K number of constraints, again you have x as the decision variables, d as the deterministic parameter values, and p is the probabilistic parameter values. In this second set of k, capital K number of equations, we will consider that the probabilistic part is not there, hence p may be 0, such that we have deterministic constraints. Again it is greater than, equal to, less than Ck, which C is basically the right hand side of the equality equation which you have. Here we will consider x to be of dimension n, that means you have n number of variables to solve, decision variables to solve. D, the deterministic variables would be in the m dimension. This m and n has nothing to do with the m and n which I have considered in the matrix multiplication. And P, the parameters which are non-deterministic, actually later on, but still in this set of problems we will consider them to be 0 in the case when you are considering the deterministic problem. L is the dimension of P. Here I is equal to 1 to I, capital I, depending on the number of such objective functions which you have. Small n is equal to 1 to n, small m is equal to 1 to m, and small l is equal to 1 to capital L. So, what are these variables? F I, I am not talking about what is inside, x, d, p are the decision variables, deterministic parameters, probabilistic parameters, is a linear, non-linear objective functions of capital I in number. So, we will consider the linear part with one objective function for the simplex method. Gj's again function of x, d, p variables, deterministic, probabilistic parameters are constraints where Bj are deterministic in nature. The second part, okay, I basically swapped the explanation of the deterministic and the probabilistic one. Hk's would basically be again the equation on the left hand side, which basically is a function of x, decision variables, d, deterministic parameters, p, probabilistic parameters, and the constraints would be equivalent to Ck, which are probabilistic in nature and they are capital K in number. Similarly, for the first set of constraint is capital J in number. And as I mentioned, x, d, p are the probabilistic control variables. I am mentioning that time and again, please bear with me. D is the deterministic control variables and p is the probabilistic exogenous parameters, where the size of x, d, p, which depends on the dimension, is capital N, capital M and capital L. Bj is the input deterministic parameters, which is very apparent from the explanation which I gave, and Ck is the input probabilistic parameters. Here x, d, p, b, c may be continuous, discrete, integer, binary, positive, whatever it is depending on the scope of the model. For the case of the linear programming, we will consider the continuous one and positive integers. If you remember, x1 and x2 is greater than or equal to 0 and x1 and x2 are continuous. For the case if I mentioned, I am mentioning time and again, if it is a problem of solving trying to find out the amount of production of paints, it was continuous, but if you are trying to find out the number of trucks which will be utilized to transport goods or the number of factories which will be built, it is integer in nature, or the number of boxes would be transferred, would be integer in nature. It can be binary, build a factory, not build a factory, build up the road, not build up the road. So, it would be 0 and 1. And I said and integers, obviously I gave the answer, binary obviously I gave the answer, positive would be also applicable. The problem formulation would be multi-objective if I is 2 or more. Now, we will basically give the concept of a slack and a surplus, and why slack and surplus will be applicable, you will understand it very simply. So, this is from the solution technique. So, consider it has nothing to do with the objective function. Consider the constraints are given as 2x1 plus 3x2 is less than 6, x1 plus 7x2 is greater than 4 and x1 plus x2 is equal to 3. Now, if you see the first constraint and the second constraint, the left hand side is lower than 6 or equal to 6 depending on some combinations of x1 and x2, but not for all. For some maximum apart from 1, for the rest of the values the left hand side would always be less than 6. So, some amount has to be added which we will consider as the slack, such that it when it is added to the first equation would make the equality hold true. So, this x3 would also change its variables such that depending on x1, x2 and x3 the equality can be held for the first equation. Similarly, when I have the second equation which is greater than 4, I basically need to add a surplus such that the variable which is x4 would basically bring the equality in the second constraint. So, there would be some values for x1, x2 and x4 such that the equality would hold true. Now, look at it very carefully. If you had an equality sign in the first equation, second equation and third equation was not there. So, your actual equation would be 2x1 plus 3x2 is equal to 6, x1 plus 7x2 is equal to 4. You solve the problem, get unique solutions x and x2 and your simultaneous equation is solved and you are happy. Now, consider these inequality signs comes. So, the moment you want to solve them using the equality one, you need to add, as I said, x1, x3 and x4. Now, when x3 and x4 are added to the first and the second and not added to the third one, actually what the third one is doing and how you formulate would be, you will basically have 3 equations. First equation corresponding to, I will just mark them. So, this would be the first equation, this would be the second equation, this would be the third equation. So, m would be 3. Now, let us add the slack and the surplus. So, if I consider the slack and the surplus for both all the 3 equations x1 of first, second, third. So, the first equation is actually converted into 2x1 plus 3x2 plus x3 is equal to 6. Second equation, when you add the slack of the surplus to convert the greater than equal to sign to equality sign, it will be x1 plus 7x2 plus x4 is equal to 4. And the third one which I have not written, actually when the surplus and the slacks are added in order to make sense in this equation would be actually x1 plus x2 plus 0x3 plus 0x4 is equal to 3. So, the number of n in this equation would be 4, n is 4, m is 3. So, if I have the actual equations written in front of me, I will just write it in the slide and make you aware of that. That is what is the matrix based on which you will start the solution. So, I am using red color. So, it will be 2x1 plus 3x2 plus x3 plus 0x4 is equal to 6. Second equation becomes x1 plus 7x2 plus 0x3 plus x4 is equal to 4. And if I come to the third equation, it will be x1 plus x2 plus 0x3 plus 0x4 is equal to 3. So, if I consider the whole set of equations, so it will basically have 3 as m, 3 equations, 4 as n, 4 variables. If I write the resulting x, a, x and b are now written, the matrix A would have basically 2 as the value which is multiplying x1, 3 as the variable which is multiplying x2, 1 and 0 are for x3 and x4. Similarly, for second equation the values are 1, 7, 0, minus 1, because when you are converting into the greater than sign and the less than sign, you have to bring the equality. And the third equation is 1, 1, 0, 0, 0, 0 being for x3 and x4. So, the b values are 6, 4, 3, and if I want to solve the problem, consider I can do it like this. One solution can be 0, 0, 6, minus 7, that means the values of x1, x2 is 0, slack and surplus values are given as 6, minus 7. So, the difficulty arises because slack and surplus variables are not all non-negative or at the best 0. So, they have to be non-negative in order to basically give you the impression that the basic solution is true. Solution to the set of constraints is true if all slack and surplus variables are non-negative. Here one is non-negative, it is negative. So, if there is a solution having all slack and surplus variables non-negative, then only the set of constraints by themselves are inconsistent, hence you would not be able to get the actual solutions to start with. So, with this I will end the first lecture in the 4th week, which is the 16th lecture, and continue discussing more about the constraints and the feasibility of the space, and then how we will use the simple Gauss Jordan to solve the problem. Have a nice day and thank you very much.